quantum cryptography. That is, we will learn how to exploit quantum mechanics for cryptography purposes. And I think also we will do a little bit of relativity in it. I don't really understand how you can combine quantum mechanics and relativity without getting loop quantum gravity or string theory, but I guess we will find out. And our teacher today will be Christian Schaffner, who is currently at the University of Amsterdam. Please give him a warm round of applause.
Thank you. Thank you very much. So, waiting for my slides. Here we go. I work at QSoft, which is a recently established research center for quantum software in Amsterdam. And as you just heard, I'm also at the University of Amsterdam, and I collaborate with CWI. I'm very happy to be here and tell you a little bit more about my field of research, quantum cryptography, for the next hour or so. And so to get started, please put on your 3D glasses. Oh, you didn't bring any. I'm sorry for that. Doesn't matter too much. I'll put on mine, so we're fine. Ready? Good. So here we go. In 1969, man has first set foot on the moon, as you can see here on this picture, sent around the world by NASA. But maybe they haven't, actually. So if you believe this kind of conspiracy theories here on the internet, then this scene has actually been filmed in some Hollywood studio. This is all fake. And this leads to one of the research questions that I'm investigating, namely, how can you actually prove that you are at a specific location? So I will come back to this question a little bit later in my talk. First of all, here's a quick outline of what I want to cover tonight. So talking about quantum cryptography, we can't do without telling you a little bit about quantum mechanics. So this is going to be the first part of my talk. And then I'm going to focus on two applications. The first one will be quantum key distribution, and the second one will be position-based cryptography, basically coming back to that question that I just asked. So here we go. Introduction to quantum mechanics. Now, for the purpose of this talk, you can think of a qubit, a quantum bit, as the polarization of a photon. Mathematically speaking, we're talking about the unit vector in a two-dimensional complex Hilbert space, but don't worry, we're going to make it way more practical. Photons are just particles of light, so imagine you can have a light source, you put some polarizing filter here, and then this direction of this polarizing filter, basically it will be the state of the qubit. So it will be this vector. You can actually turn this around, so this vector has length 1. And in quantum mechanics, we kind of give some particular names to certain directions. For instance, this horizontal direction here, we're going to call the 0 state. So just basically arbitrary naming, we call this the 0 state, and we use this fancy notation with these brackets to denote that state. In my talk, I'm just going to use this symbol here, so this round symbol with these horizontal arrows, that's going to denote the 0 state. And actually, so the actual direction doesn't matter, so it doesn't matter whether it points here to the right, it may also point to the left. We're just going to work with, say, the horizontal way of polarizing photons. Now, the polarization which is orthogonal to that, we're going to call the 1 state. So here we have another state of our qubit. And together they form a basis, or orthogonal basis, of this vector space. And we're just going to use, say, the yellow color for it. This is called the rectilinear or the computational basis. Let me get a little bit more practical and actually build this thing. So we need a light source. But wait a second, there's light sources all over the place. Actually, I'm holding a light source here in my hand, so this laser, perfect light source. Now we need a polarizing filter, and that's the time when you can take off your 3D glasses again. And actually, next time you go to the cinema, just grab some of them instead of delivering them at the end of the show. Grab some extra ones because they're actually really useful. You can destroy them like this and take out the polarizing filters. And so, doing that, we can actually build such a quantum system. Here I have a light source, I hold this polarizing filter in front of it, and I can turn it the way I like. And I basically built that system. So let me show you that a qubit, a quantum bit, is at least as good as a classical bit. So here we have our two heroes, Alice and Bob. Alice would like to communicate a bit to Bob. Now what she could do is she could take her light source, use a polarizing filter like that, and send that to Bob. Now Bob, on his side, he could put another polarizing filter in the orthogonally polarized, and if no light comes through, then he doesn't see any photons, then he would say, well, Alice was actually sending a zero state. So I have prepared this little experiment over here. Now maybe you can switch to the camera. So I have a laser pointer here, another one. And I'm shining, oh yeah, I'm using little polar bears for polarization. You can get them very cheap if you go Christmas shopping now. So here's the laser. I shine through both of these lights, and you see over there, right now Alice is sending a 0, and this other filter is 90 degrees polarized, so there's basically almost no reflection here in the ground. If I turn this, then actually you see this point there is getting much more brighter. So here we're about, it's not a perfect filter, but it's pretty good. So now the light is almost gone. Okay, you can see, so maybe switch back to my slides. You can see, using this technique, we can send classical information from Alice to Bob. In particular, if Alice is sending the 1 state, then if Bob puts his filter, the light will go through, and therefore, if he sees photon, he knows Alice was sending a 1. So we can use qubit to send zeros and ones. And in fact, what we're doing, quantum mechanically speaking, is a so-called measurement. So Alice is sending a state, and we're doing a measurement in the computational basis. The outcome of a quantum measurement is a classical bit. It's either 0 or 1. And this happens with a certain probability. In this case, if Alice is sending the 1 state, then with probability 1, Bob will actually get 1 as an outcome, and nothing changes in the state. So far, so good. Now let's do something more interesting. And what you can do with a qubit is that you can not only polarize it, say, in these 2 directions. What you can do is you can do stuff in between. You can just rotate your filter arbitrarily. And we're going to call this state, which is kind of 45 degrees between 0 and 1, we're going to call that 0 state as well, but in another basis, namely in the diagonal basis. So we have 2 more states, this one and that one. And we're going to use the red color for that in this talk. And so these are these 2 states here, the 0 state in the diagonal basis and the 1 state in the diagonal basis or Hadamard basis. And together they form this another orthogonal basis. So this state, the 0 state, in fact, in terms of linear algebra, you can interpret it as a linear combination of the 0 and 1 state. So if you take this vector here, 0, and you add 1, and you properly renormalize to have a unit vector, then you actually get that 0 state. So in fact, what we have is actually a superposition of 0 and 1. So we have a qubit in a state which is both 0 and 1 at the same time. Basically just using this diagonal polarization. Now, what happens if we go and measure that state in the computational basis? So again, the outcome will be a classical bit, but now we're going to have a probabilistic outcome. So imagine, what happens if you send like diagonally polarized light and you put this filter, like Bob did before, then roughly half of the light will go through. Now, you saw me turning before, and the pulse was getting fainter. So if you turn like 45 degrees, then roughly half of the light will go through. I would have to do this experiment with single photons, but then you can't see anything anymore. So, in fact, what quantum mechanics tells us is if you measure that state in the computational basis, you're going to get a random bit as outcome. With probability 1/2, you're going to see a 0. And in fact, you're changing the state by observing it, by measuring it in space. And because after you've seen a 0, then the state is actually the 0 state. On the other hand, if you, with probability 1/2, you will get outcome 1, and you change the state to 1. So whatever comes out of this filter is actually polarized in this vertical direction. Now, let me show you the following, and this one can actually demonstrate. I'm going to go back to the experiment. So, Sorry for all the work over there. Thanks a lot. So this same setup as before. You see hardly any pulse on the other side, because it's now 90 degrees. So if I turn, it got brighter. Now, so it's almost gone now. What I'm going to do is I'm going to take another filter, and I put this in between those two filters. And what's going to happen is that the point actually reappears. You see? So this is something very strange, no? You have like, nothing goes through, and you put something more in between, and actually it's going to reappear. Right. So what's going on here? So if you go back to the slides, here's the explanation. So we started off with something that is polarized horizontally. And clearly, if you put something 90 degrees, you don't see anything. That was the setup. Now, what we did is the following. We put another filter in between, and it turns out that the zero state, you can see it as a superposition of this diagonal zero state and the diagonal one state. So it's a linear combination of these two. It's a superposition of these two. And once we put this diagonal filter in between, we actually measure in that basis, for instance, obtaining the zero state, only letting light through that is in this direction. And in fact, as I said before, I have changed the state to that. So I've changed the polarization of the light. Roughly half of the light is going through from this horizontal direction to the diagonal direction. And now, of course, if I put the other filter in between, now then roughly a quarter of the light is actually going through. No? So by putting something in between, actually demonstrating that measurement actually changes the state. Because again, you can interpret that diagonal zero state as a superposition of the other two. If you're going measure, you actually end up with something. Yeah? So here, that's the magic of quantum mechanics. Thank you. So here's a quick summary. What we've learned so far, there are funny states. You can actually produce them. It's not that hard. We use the yellow and the red color for it. What you can do is you can measure them. Let's take the one state, measure it on a computational basis. You will get with probability 1, outcome 1. You don't change the state at all. If you happen to measure the state in the wrong basis, say this one state in the diagonal basis, your outcome is a random bit. With probability 1/2, you see 0, and you change the state to the 0 state. And with probability 1/2, you get a 1, and you change it to the other state. So that's basically all you need to know for now. And with that in hand, we actually enter the wonderland of quantum mechanics. We've already seen stuff that can be 0 and 1 at the same time. It's kind of a superposition of 0 and 1. And in fact, here is Schrödinger's cat, you might have heard about. This is a thought experiment, a Gedanken experiment, where you have some, say, qubit that is in a superposition of 0 and 1, and it kind of, in this box, there's a setup so that, say, conditioned on the outcome being 1, there's some poison released inside this box that will actually kill the cat. And if the outcome is 0, then nothing happens, and actually the cat is alive. So Schrödinger thought of this experiment, don't do that at home, of this box, where inside this kind of superposition should extend to this macroscopic object of a cat, which is both dead and alive at the same time. So this hasn't actually been observed in reality yet, but there are superpositions of, say, molecules, for instance. So not cats, but maybe we'll get there at some point. With these things, you can build quantum computers. So maybe this is maybe a picture of the currently largest quantum computer we have. You can count them. There's maybe 9 qubits. This is from the UC, from a group of Joe Martinez at UC Santa Barbara. They were bought by Google. So there's a lot of development in this area, but that's not where I want to go in this talk. I'm going to focus on this part here below, and I'm going to explain you later in my talk what these things are all about. So I would like to give you another little demonstration. Here I have a black box in my hand here. So this is a physical random number generator. It's connected through a cable here to the USB port of my computer. And what I can do with it is I can create random numbers. So let me switch to the application that does that. Now, basically, here you don't see much. There's just a green LED flashing here, and it's connected here. You can see the serial number, then I can choose what I want to do. Let's say I create integer numbers between 0 and 1, so bits, maybe 1,000 of them, and press generate. And here we go. Random bits that nobody has ever seen before. Great. Thank you. So how does it work? If you look that up and go to the producer's website, ID Quantique in Switzerland, they tell you that inside this box, there is a light source, like this one that I'm holding in my hand, a laser, that emits qubits, like states that we have seen before. And they're shot onto a semi-transparent mirror. Again, this is like nothing fancy, actually. This semi-transparent mirror, it lets the photons either go through to this side or being reflected to the other side. And this should happen roughly with probability 50%. Here are some photon detectors that detect which side they took. And then there's some classical post-processing. And in the end, you end up with random numbers. So there's a lot of stories to tell about this device. Again, unfortunately, I don't really have time for that. However, the point I want to make here is that for this, you don't need any quantum computer. So there's no quantum computer inside here. There's basically just technology that we can actually build. The only thing we need for this is quantum communication. And so this is something that we can actually do nowadays. So I get slowly but surely to the first application, namely the one of quantum key distribution. And here is, let's move the pointer away. In order to understand that, there's one more thing I need to tell you, and this is the so-called no cloning theorem. So this is a mathematical statement that says the following. Let's take one of these 4 states at random. Let's notice with this question mark here. So this is just selecting one of these 4 states at random. And the goal is to make a clone. So this is Dolly, the sheep. We know how to clone sheep. And the goal of this task here is to clone an unknown quantum state. So take an unknown quantum state, try to come up with a machine that makes a perfect copy, a perfect clone out of this state. Now, it turns out that quantum mechanics does not allow us to do that. So given whatever we can do by quantum mechanics, measurements, unitary operations, whatever, we will not be able to do this, so there exists no cloning machine. And this is the no cloning theorem. And the proof of it is actually pretty easy. You can do that after, say, 2 hours of linear algebra, because it turns out that copying this operation here is simply a nonlinear operation. And you're only allowed linear operations by quantum mechanics. So it's really pretty easy to prove that, say, in 2 lines, if you know how to formalize this properly. And somehow intuitively, you're forbidden to make a copy, you're forbidden by law, by nature, to make a perfect copy out of a state. So this smells already a bit like cryptography, you know? We should be able to use this in order to kind of secure information. And indeed, that's what we can do. So 2 clever people, Charlie Bennett and Gilles Brassard, back in '84, they came up with this scheme. This quantum key distribution, QKD scheme, between Alice and Bob. It works like that. There's a quantum phase where Alice sends some qubits to Bob. So these are these dashed arrows here. And then they talk classically over an authenticated channel. And so there's an eavesdropper. The eavesdropper tries to kind of listen in this conversation, and she has full control over the quantum part of this transmission. The classical part is authenticated. That means Eve is able to read, to hear everything that the players say, but she's not able to change the messages. In this setup, the goal is to come up with a key, a classical key. So this is just a classical bit string, which is identical for Alice and Bob, something like that. And Eve has no clue what it is. So whatever she does here, she will not be able to learn that key. So this is a key distribution protocol, and I'm going to explain in a second how this works in more details. But this offers a quantum solution to the key exchange problem. And the funny thing is kind of that it does not rely on any computational assumptions, such as factoring, discrete logarithms, security of AES, or SHA-3, etc. One can mathematically prove that this scheme is secure. And it's a key exchange setting, so it puts players into the starting position to use symmetric key cryptography. So once you have established the key, then you can go and do your favorite task. Say encryption, you can use, say, the one-time pad with that key that you generated here. So in order to put this a little bit in perspective, I've created this slide here. So the quantum cryptographic landscape, also naming other things that have been covered here at this Congress. So here on the x-axis, there is the power of the attackers. So I'm considering here efficient classical attackers. And efficient, I mean polynomial time, so attackers that run within like reasonable time frames. Classical ones, or in as opposed to quantum attackers, where they can use quantum computers, but still they have to run efficiently. And then there's the funny last column, which is called everlasting security, so a term that means that you're allowed to store whatever is communicated on the line, and then later, at some point in the future, actually after an infinite amount of time, you can break it. And therefore, all these things will fail to a brute force attack. So if you look at AES or SHA, then we're pretty confident that this is secure against efficient classical attackers. I mean, there's no proof for it, but that's what we believe. People have looked at this for long. They probably also secure against quantum attackers. You just have to make sure that you use long enough keys, and in case of hash functions, that you use long enough outputs. But of course, they will fail against somebody who has just an infinite amount of time. If you saw Dan's talk and Dan and Tanya's talk yesterday, then there's Shor's monster here. So this is this big red box here, where that will come and break RSA and discrete logs. So everything, basically every public key crypto system that is currently used on the internet will be broken by efficient quantum attackers, whereas we are confident that they resist classical attackers. And then the area of post-quantum crypto kind of kicks in and tries to fix that, and coming up with different new schemes. And this was the topic of Dan and Tanya's talk yesterday, namely hash-based signatures, the McAleese encryption scheme, maybe lattice-based crypto. But more research needs to be done in order to really be more confident that these schemes actually do resist classical as well as quantum attacks. Now, what I'm going to talk about and what my research is about this last column here. And this is basically using more technology on the honest player side, so it becomes more difficult, technically speaking, and also money-wise, to implement these things. For instance, you can use QKD, which we can mathematically prove, because we don't rely on any computational assumption that it's secure. And what I see as the biggest advantage of a QKD system is that the attacker actually has to act while the protocol is running. So it really has to kind of attack it at the moment when it's run. And if this attack is not successful, then from that point on, whatever key is generated will be secure forever. And so, of course, it's interesting to kind of take this technology, if you can afford it, if you can somehow implement it, and combine it with say, more conventional schemes to actually get the best of both worlds. And that's also how current implementations do it. All right, so let me explain you in a bit more detail how it works. So in this protocol, in this BB84 protocol, Alice starts off picking random bases. So she picks a string of, say, red, yellow, yellow, at random. She also picks a random string of bits, say 0, 1, 1, 1, 0, and then she encodes these bits into that basis. So we get back this kind of one of the 4 states we've seen for each position as before. And that's what Alice sends over the quantum channel to Bob. Now, Bob, he has no clue what these colors are. He cannot see that from the qubits that he receives, and so he has no idea what the basis is that Alice was actually using. And what he's going to do is just pick another random basis. So he picks another basis at random, say yellow, red, red, yellow, yellow, and measures in that basis. So he doesn't need to store anything. He can just do this beforehand, and as soon as the qubit arrives, he can measure immediately. So it turns out, if he was lucky and he picked the right basis, well, then he will also recover the right bit. That we have seen how that works. If you happen to measure in the wrong basis, say you a yellow qubit in the red basis, well, then you just get a random bit, which might agree with what Alice had in mind, but it also might not. So we don't know. So how to kind of solve this problem? Well, Alice is going to classically tell Bob, say, hey, look here, this is the string of bases that I was using, say red, yellow, red, yellow, yellow. And now Bob knows where he actually measured correctly. So he sees, oh yeah, these first two positions, they were no good. I measured them in the wrong basis, so let's throw the results away and just keep the rest, where I measured in the correct basis. So he also has to tell Alice about that. So classically, again, he can tell Alice, hey, let's throw away the first two positions. I didn't measure there correctly, so let's just throw those out. Okay, and what remains, they basically have as key. So that becomes the key that they're sharing. But wait a second, it's not that easy. After all, there's the eavesdropper. So, as I said, the eavesdropper has full control over this quantum communication here. And that means that, well, luckily, we kind of try to use this no-cloning theorem because, well, Eve doesn't know the basis either, so for her, it just looks like one of these four states picked at random. And we've seen that the no-cloning theorem actually forbids her to make a perfect copy out of it. Classically, you could just copy everything that flies by on the line, and you would be exactly in the same position as Bob is. However, quantumly, it's not that easy because you cannot simply make a copy. And therefore, that's the tricky part, the honest players, Alice and Bob, they can actually test whether somebody has interfered. Because Eve can try to make a copy, but we've seen kind of measuring, observing a state actually changes the state. And therefore, there's a kind of a trade-off. The more she tries to learn about that state, the more she will actually interfere with it. And therefore, there will be errors in that remaining part here. And so in an additional step in the protocol, the Alice and Bob, they're going to check classically how many errors approximately are in the remaining string. They will correct for that. They just use classical error-correcting codes. And then they do another step called privacy amplification. They basically hash it down to something smaller. And all this together will actually make sure that, so they might have to sacrifice some more positions. They might have to apply some additional operations. But they eventually end up with a smaller key about which we can guarantee, we can actually mathematically prove that Eve doesn't know anything about it. So in order to do this, this is really pretty tricky. So mathematically speaking, you actually have to follow, say, a whole course about quantum information theory in order to give a mathematically sound proof of this statement that I just outlined here. But intuitively, yeah, it's not that hard to grasp. All right, so as I kind of showed with this device, this is something that we can actually do. The honest players, they only need to generate some photons, polarize them. I've done it over there. And Bob, he just needs to measure them upon reception. So it's technically feasible. We don't need any quantum computer. Well, Eve might, but we don't care. I mean, we only care about the honest players. We only need quantum communication. And in fact, this company that's producing these random number generators, it's not a coincidence, they also produce quantum key distribution devices, like this one over here. So that's something that you can actually go into a store or a web store and buy it. It's pretty expensive. However, these devices are out there, and that means that they can also be hacked. So you could just go and open this thing up. It will look like that inside. And it's an older model. But these kind of standard rack-sized black boxes that are connected by some optical fiber, and well, commercially available. That means there's also people who actually hack them. So this is a picture of Vadim Makarov. He's originally from Russia, he's now at the University of Waterloo. He runs a quantum hacking lab. And he has opened, so this picture is done by him, he has opened these devices, also the random number generator, of course. And here's a little picture of him actually at a camp in the Netherlands, at Haar, hacking at random in 2009, where he brought his little suitcase, well, his eavesdropping suitcase that allowed him to actually hack commercially available QKD systems. I don't want to know how he got through customs with that, but he actually managed. He has lots of stories to tell about this, actually. Okay, so that's kind of the state of the art of quantum key distribution. And yeah, I think I'm approaching the last part of my talk. So I'd like to come back to this question. Remember the question? The moon, yeah. How can you actually prove that you are at a certain location? So let's see. Well, normally, cryptographic players in a perfect theoretical world, they use credentials, cryptographic credentials, such as, say, secret information, a password, or a secret key that you store in some safe place, or, say, authenticated information like a passport, or biometric features like your fingerprint, your iris scan, something that distinguishes you from the rest of the crowd in this audience. The question I would like to ask here is, can the geographical location of a player be used as such a cryptographic credential? So is it possible to use just the fact that I'm on the stage and almost nobody else is? Can that kind of distinguish me from all of you? First of all, this sounds like a bit of a strange question, but if you imagine, say, the setting of a bank, where you just walk in and you see some person behind the counter that you've never met before, just the fact that this person is standing behind the counter kind of makes you trust this person with all your financial details. No, of course, the bank has made sure that only trustworthy people, hopefully, are actually behind the counter. But nevertheless, it's kind of the place where this person is that makes a difference. Maybe other applications, if you are able to answer this question, is like, have you ever been to the moon? Are you actually on the moon, for instance? Or, say, in a military context, you want to make sure that a launching missile command actually comes from within your military headquarters and not from some nearby terrorist cell. Maybe in the setting of this Congress, you want to broadcast a message and you want to make sure that only at one particular assembly it can actually be read. Wouldn't that be fun? Maybe you can try to kind of avoid this so-called pizza delivery problem, or avoid making fake calls to emergency services, like this poor guy over here who has been swatted by some fellow gamers. And more, many more. You know? So like, try to think of some nice applications and let me know if you come up with them. So let's try to do this. And of course, so this now something happens that we always do if you kind of cook up a new question. We abstract away all the noisy details and we kind of try to simplify our world as much as possible. And we study the very basic task of position verification. Additionally, I'm going to assume that everybody involved lives in one dimension, just on this line here. Of course, that's not realistic. Actually, we live in 2, maybe 3D, maybe 4D. But for now, just assume that everybody lives on this line. We have 2 verifiers, and we have some prover in the middle. And the prover would like to convince the verifiers that she is at this particular blue line here. And this is a publicly known place, so everybody knows where this blue line is. And what we want to make sure is that no coalition of fake provers, and I'm going to call fake provers everybody that is not at this blue line, except the verifiers. So for instance, evil Alice and evil Bob, even if they collaborate, they shouldn't be able to convince the verifiers that one of them is at this blue line. That's going to be the task I want to solve. And even more unrealistically, I'm going to assume and make a lot of oversimplifying assumptions. For instance, that communication between the players is going to happen at the speed of light, which is actually not true in reality. You know, if you send, even if you send information through optical fibers, it travels at less than the speed of light. I'm also assuming that actually computation is instantaneous, doesn't take any time to compute anything. Of course, that's also not true. And I assume some back channels for the verifiers that somehow they can coordinate their actions. This is less of a point. OK, let's try this. Let's try like that. So the first try goes as follows. Let's say time goes downwards. And we have the following protocol. Verifier 1 picks a random nonce, some random string x, and sends that to the prover. The prover is simply asked in the protocol to return that string x back to the verifier. And the verifier measures the time it takes for the string to come back. So, this technique is called distance bounding, because it allows you to upper bound how far away the prover is from this verifier. Imagine if the prover is further away, then it will take this message longer to get to the prover and also longer to return. So if you know when the message arrives, and if it's the original message, then you can somehow put an upper bound on how far the prover is away. And so if you do this also from the other side, let's say we choose another random string y and let the prover return it over there, again, we'll measure the time it takes, then hopefully you are able to verify that somebody is at this blue line. So let's try to break this, setting up our evil Alice and evil Bob. And actually, it's not very hard to break this protocol, because what they can do is Alice can intercept this classical message x, and they know where this blue line is, so they know when the honest prover would return it, so they just waits for the right amount of time and returns that message back to the verifier after that amount of time. And Bobby does the same thing. Intercepts y, he waits a little, sends that back to y. And to the verifiers, this looks exactly as if somebody has been at this blue line. So they cannot distinguish this situation of the attackers from the situation when there is an honest prover at the blue point. So they completely break this protocol. It doesn't work. Let's have a second try, something more clever. Let's send this x and y, still classical inputs, so that they arrive at the same time at the prover. And let the prover compute some function on these inputs. Let's say the prover is supposed to check whether x equals y. Let's say a is equal to b, and it's equal to the bit that says whether x is equal to y or not. Then the prover, but it can be an arbitrary function that is easy to compute. So then the results would have to be sent back to the verifiers. The verifiers, they would check the time it takes for the messages to come back. So computing doesn't take any time. That's what we assumed. We know how fast the messages travel. So hopefully that will work. Let's try to break it. So let's set up Alice and Bob. Now, what do they have to do? Yeah, suspense. So Alice can intercept this x. You can make a copy out of it. It's a classical string, so she can keep a copy for herself. He can send another copy over to Bob. And Bob, he can do the same thing. He takes this y, keeps a copy for himself, sends another one over here. And now, just in time, they both have x and y. And they just go along and basically compute the function themselves. So this is a publicly known function, say, equality function. Alice can check whether x equals y and send that outcome in time back to the verifier, and Bobby will do the same. So again, complete break of the protocol. Doesn't work. However, and in fact, it turns out this is a generic problem. Actually, no protocol for classical position verification in this setting will work. So these people here have shown, actually I should say, all these references are actually hyperlinks. If you download the slides, you can click on them. And it will take you to the research paper, which shows that actually this is a generic problem. So you can never have any classical protocol that is secure in this sense. And this holds not only in one dimension, but in arbitrary dimensions. Because simply you can set up attackers between the claimed position and the verifiers. They intercept everything that comes along and forward it to their fellow cheaters. And they will be able to run the same function as the honest prover is supposed to run. And thereby making it look to the verifier as if somebody was there. So this doesn't work. However, if you look at the attack, so that's what they're doing. No, they're kind of taking a copy of this x and share it with their fellow cheater, and then compute the function themselves. This involves copying classical information. And of course, we have seen quantum no-cloning theorem. So turns out that maybe we should use quantum information, and we should make it hard. You should make it impossible for Alice and Bob to do this copying operation. So here we go. Let's try that. Let's have the following protocol. The first verifier sends say, a random qubit. This question mark can be, say, one of these 4 quantum states we've seen before. Sends that over a quantum channel to the prover, and timed in the way that it arrives at the same time at the prover, the other verifier sends a classical bit, just one bit, 0 or 1. If the bit is 0, then the prover is supposed to send it back to the first verifier. You can just put the mirror, and then it will be reflected back to the first verifier, who again will measure the time, will make sure it is the original qubit that was sent. Well, let's assume that's not a problem. Then if the bit is 1, it's supposed to do nothing. Just let it pass through and kind of let it fly to the other verifier over here. So that's the protocol I want to look at. And let's try to break it. So here is the game that we have to play as attackers. Alice has a qubit, Bob has a classical bit. And if the bit is 0, Alice needs to end up with a qubit. If the bit is 1, Bob needs to end up with a qubit. So Bob just has classical information. He can do the same thing as before. He can make a copy out of his bit, keep one for himself, forward one to the other side. But Alice, she's in trouble. Now, because of the no cloning theorem, she has to kind of try to make a copy here, which she cannot do due to the no cloning theorem. She's kind of, by the timing constraints, she's forced to make up her mind right now, right here, at this point. But she doesn't know yet whether the bit is 0 or the bit is 1, because it takes some time for this information to travel over here. So she could, of course, she could guess. She could say, well, the bit is probably 0, I keep the qubit for myself, and half of the time she'll be lucky, and she can send the qubit back. But the other half, she doesn't have it. The Bob needs the qubit, and it's too late to send it. No, it would arrive too late, so the other verifier would notice. So it looks like this is secure because there is some certain probability that things will go wrong. There's a non-zero probability that the verifiers can distinguish this situation of the attackers from the one that with an honest prover in the middle, who will always succeed. It was very easy to run this protocol honestly. You can just put the mirror or not, and he will always succeed. So there's a gap between these two probabilities. So if you repeat it, say 1,000 times, 1,000,000 times, then at some point, very quickly actually, the verifiers will see a difference between this setting and the other setting. And so that would actually prove security. That's what we thought. Turns out it's not true. Actually, you can break this protocol, and you can even break it perfectly. So this was quite a blow. I mean, we thought, no, that cannot be. And in order to understand how to break this protocol, I need to explain you 2 more things. I need to explain to you what EPR pairs are, because they need kind of a magic resource, Alice and Bob, in order to do that. And so EPR pairs, they are named after these 3 very famous physicists, Einstein, Podolsky, Rosen. They come in pairs, that's why they're called pairs. And they somehow haven't made up what they want to be. So there's all these arrows here. Somehow it's kind of a mixed state. And there's this magic glow between them. So they are in a very interesting, special state. They're entangled. So these are entangled qubits, verschränkt. And it's possible to generate them. So Alice, for instance, can generate them. She can keep one for herself. She can give the other one to Bob. And in fact, they can be very far away from each other. So they may be generated at the same place, but then Bob can take it with him, or say, send it over some optical fiber. It can be hundreds of kilometers away. However, they are still entangled. And what that means is that, for instance, if Alice goes and measures her qubit, say in a computational basis, then, because this guy hasn't really decided yet what he wants to be, you will actually get a random bit as outcome. With probability 1/2, you're going to get a 0, and you collapse the state to the 0 state. And with probability 1/2, Alice will get a 1, and she will collapse the state to a 1. But the funny thing is that simultaneously, when she obtains her measurement outcome, this state also collapses on Bob's side. And so this is kind of the EPR magic. So this is kind of the funny thing of these quantum states. And this is what Einstein called spukhafte Fernwirkung, spooky action at a distance. And he didn't like that. So what that means is, for instance, if Alice observes a 0, and the 0 state, and Bob's state is also a 0 state, it means if he goes and measures it again in the computational basis, he will now get with probability 1, he will get the outcome 0. He will observe the same bit as Alice did before. So to Einstein, this looked like, that's no good, because that seems to contradict my theory of relativity. However, it's actually not true. So I didn't quite understand, but these EPR pairs, they do not allow to communicate information. So it's a difference whether, so here it allows them to get a shared random bit, because when Alice measures, she will get a random bit, and Bob, when he measures, he will also get the same random bit. So it's just a shared classical random bit. It's not information that Alice had in mind, say, I want to send a 0 to Bob, because once she does her measurement, the outcome will be random. And that's the difference between sending information from Alice to Bob to just creating some shared correlation. Now, probably this is hard to grasp, and don't worry, very smart people had trouble with that. So if you see this for the first time, relax. So it's okay. If you have this, then we can actually do quantum teleportation. So we're not going to do the Star Trek version. We're going to do the version that was cooked up by these people over here. Actually, a long time ago, 93. It works as follows. So let's say Alice and Bob, they have such an EPR pair. Actually, this has been demonstrated many, many times experimentally. So this is something that you can actually do. They share an EPR pair. They might be far away from each other. And on top of that, Alice has an unknown qubit. And that qubit, this qubit over here in this unknown state that she doesn't know, she would like to teleport to Bob. So she would like this qubit to end up on Bob's side. Now what she can do is she can do a kind of complicated measurement that I haven't talked about on her 2 qubits. So she will do a so-called Bell measurement. And this is a measurement on 2 qubits. It's the half of the EPR pair that she shares with Bob, together with the qubit that she wants to teleport. The outcome of this measurement is again going to be classical. It's classical 2 random bits, actually random bits. So say 0, 1, 2, or 3. And magically, because of the entanglement, this qubit will appear on Bob's side. However, it will not appear in the clear. It will appear in some encrypted form. Actually, this is the analogon to the classical one-time pad, so XORing with a random bit. This is actually the quantum one-time pad, because it's actually XORed in a quantum way with 2 classical bits. Because if Alice sends this classical outcome, sigma, over to Bob, then he is able to unlock this encryption and actually recover the original qubit. So this is the procedure how quantum teleportation works. You have to do you have to have an EPR pair. You have to do a Bell measurement. You get a classical outcome. That outcome needs to be sent to the other person. And once you know that, you can undo the encryption of the state in order to recover this original qubit here. And again, this is something that does not contradict relativity theory. So this kind of collapse here doesn't happen instantaneously. You can only recover this qubit after you've learned the classical information. And so it takes some time for this classical information to travel from Alice to Bob, if they're far apart. And so there's no information going faster than the speed of light, because you have to wait for the sigma before you actually get the state that was in Alice's hand before. All right, so now with that at hand, we can break our protocol. Remember what it was, the attack. Alice had a qubit, Bob had a bit. The qubit should end up at Alice's side if it was 0. If this bit was 1, then Bob should end up with a qubit. And if they share entanglement, if they share, say, 2 EPR pairs like this, and why wouldn't they? No, they can just go and prepare that beforehand. Then they can actually perfectly break this protocol. Because what they can do is teleportation. So here we go. Alice would do a teleportation measurement, a Bell measurement, on this qubit that she holds, together with the first half of one of the EPR pairs. This will teleport this qubit over here to Bob. Now, actually, it will not be here in the clear, it will be encrypted, but these keys, you will just send these classical keys along here. And Bob, he has the bit. He knows whether he should keep the qubit or not. So if the bit is 1, he will just not do anything and wait for these keys to arrive and uncover this qubit. So then he will hold the right qubit. However, if the bit is 0, then he will actually teleport it back to Alice. He will just do another teleportation measurement and kind of make this qubit now end up again on Alice's side. So it's at the right place. Now it's kind of double encrypted. It's encrypted by this measurement and by that measurement. But again, there's time for this classical information to travel. So he would send along B, and he would send along the outcome of this measurement. And then Alice, at this point, she learns, oh, B0, so I have to look at my second qubit here, and I have to undo this measurement here that Bob did to uncover, and then I have to undo my own measurement that I did, and I will end up with the correct qubit. So hereby, you actually perfectly break the protocol, because again, to the verifiers, it's going to look as if somebody is in the middle. So, well, are there actually protocols that cannot be broken? And this is kind of one of the main results we obtained in this research area. In fact, there is no secure protocol. So what we have showed is a so-called no-go theorem that we've done back in 2010, that any position verification protocol, even if it's a quantum protocol, it can be broken using a huge number of entangled qubits. So if you have enough resources, an exponential amount of resources, then you can break any of these position verification protocols. However, as always in science, if you kind of answer a question and you prove a theorem, it immediately leads to new questions. And here, the obvious question is, well, do you really need that many resources? Or is there a protocol such that it's easy to run if you're honest? So honest provers and verifiers are efficient. So they just need to do simple things. But where we can guarantee that any attack on it requires a lot of entanglement. Well, that would be great. Then we actually have a secure protocol. And this is actually a research question that I'm currently studying. And I invite you to have a look at my homepage for some recent developments in this area. I think that brings me to the end. I hope you've learned something in this talk. First of all, about quantum mechanics, what qubits are, these 4 states. You've seen the no-cloning theorem. You've encountered some funny new resource state, qubits that are entangled. And you've seen how to use them to do teleportation. In the first application, I've talked about quantum key distribution and tried to give you a little bit of context where it fits in the world. And in the second part, I've talked about position-based cryptography, one of the currently active research areas, where it depends whether you can break the protocol if you have enough resources, and maybe you cannot if you don't have enough resources. All right, thank you very much for your attention. And
we now have some minutes left for Q&A, so please line up at the microphones. This is an exceedingly well-mic'd room, so you have 8 microphones to choose from. Just line up at any one of them, and I will call you when you can speak. Yeah, and please try not to walk in front of the cameras when you leave. This is very annoying for the people on the stream. Also, the people in the stream, if you're on the ISC channel or on Twitter, you can just ask questions there. We do have an internet person here that will read your questions. Microphone number 2, please.
Hello. Yeah, thanks for the great talk. But I have one question concerning the quantum key distribution using real machines. And you said they could be hacked. And for my understanding and clarification, I assume that this hacking does not take place at the quantum part of this process, but it takes place at the specific implementation and classic channels. Is that true?
yes, of course. So with any system you implement, even if you can show security and prove security in our perfect mathematical model, we have to make sure that we actually model the reality. And in reality, things are way more complicated. You have to use photon detectors. And in fact, in this particular case, it was the photon detectors that were attacked. So Vadim was able to actually blind them by just shining in a lot of light. So they are very sensitive. They normally operate on a single photon level. And thereby kind of getting out of the model that we use to prove security. So it's really an attack on the actual implementation. But in fact, maybe I can say in general that I see this as a sign of maturity of this field. I mean, that's the only way to go. No? Somebody has to build the machine, then somebody comes and attacks it, and kind of it's a cycle. No? And so things get better by investigating actual implementations.
Thanks.
Just a quick note to the people leaving right now. This talk is going on for like 3 more minutes, so please just wait 3 more minutes and stop being very annoying to everybody. Thank you. Internet, please.
Thank you. First question, is there anything you can do at home with limited budget?
Well, you can definitely run these little experiments that I did. You actually can have a lot of fun with polarizing glasses in general. But say of real cryptographic relevance, that's going to be way harder. Because you do, in order for these security proofs to kick in, you do have to operate on a single photon level. And this is very delicate to handle. So you need some photonic lab in order to do that.
Microphone number 1, please.
So one comment, because you were commenting on our talk from yesterday, the post-quantum talk. I mean, if you are using AES or if you're using any authentication code, you are back to computational assumptions, hardness assumptions. So when you had your overview table, you were still claiming you have infinite long-term security, while at the same time you're combining it, and that's just not true. The other comment I have is, so how about my mobile communications? How about the most common use of internet via Wi-Fi?
Okay. Concerning your first question, I think we should take this offline. I mean, I'm happy to explain it to you. Your second comment, of course, in that sense, this research is not, I'm assuming a very strong model for this position verification, where basically, as I said, I call kind of fake provers all those that are not at this claim position, and there can be even coalitions. So in that sense, it's not realistically modeling a real-world scenario.
I'm not talking about...
Into the mic, please.
I'm speaking into the mic. Okay. I'm not talking about the second part. I'm talking about like, what would QKD give me for the normal crypto applications?
Okay.
Like mobile phone and Wi-Fi.
Okay. Well, as you know, it's quite a high demand, say, on the hardware side that you have to have in order to run this protocol. Of course, there's also a lot of efforts to actually miniaturize those devices so that maybe at least one part is actually portable, in a sense. The best kind of add-on that QKD can offer is this everlasting security, that you have to kind of be actively attacking at the point of execution. And if you're not successful in that, then actually the rest of the time the security will be guaranteed.
So I will have lasers.
Sorry, we have lots of people queuing. Please discuss later. Thank you. Microphone 4, please.
Correct me if I'm wrong, but you need a direct line for this kind of thing to work, right? So if you have any routers or something in between, then it won't work, because you need to read it out or make a copy.
Just clarifying, are you talking about the second part or the first part, or both?
Both, I think.
Well, for quantum key distribution, that doesn't matter too much. So you're perfectly fine routing your cables around corners. You're using optical fibers. For the second part, it's actually kind of crucial. You're right. So it's all about timing there. So, and of course, you have to consider more realistic settings. Also, the fact that we are not communicating at the speed of light. This will add additional constraints, and so it will. Way more work is required to model, say, a more realistic setting where you might not have a straight line of sight, where the communication actually has to take some corners. And so you might end up not with one particular position you can verify, but with a whole interval, so where you can make sure that somebody is. So, but these are things that we are currently working on to model things more realistically.
Mic number 2, please.
Hello, I think Tanya had a similar question, but you said you have no computational assumptions for QKD, but you need this authenticated channel.
That's right.
And the authenticated channel, you do it with classic crypto, with either an HMAC or RSA signature, so you have the computational assumption again. So I think this whole QKD thing is kind of circular. You're trying to replace whatever, an AES cipher, but you again need some maybe a hash function or some signature from traditional crypto to make it work in the first place. So I think it's a very expensive solution for a non-existing problem.
Okay. Well, so in fact, you don't need to use a computational scheme to do authentication. There are information theoretically secure authentication schemes. But you're right that you're using up this key. So in a sense, also what you can never prevent is that Eve just completely blocks all the communication. And in that sense, she will be able to kind of make you run out of key. But what it does add is that this feature that I already told Tanya, namely that you have to be active at the moment of execution. So this is kind of the upgrade to, say, classical schemes.
Unfortunately, we are out of time, so please thank Christian again.
Thank you.